Folks, welcome back. Today we're going to be looking at torque. We've already dealt with forces, and we know that forces are responsible for changing the motion of an object. But more specifically, forces we're going to think of as changing the motion from place to place, or the translational motion of an object. But what about an object that's rotating? How do we change the rotation of an object? Well, it turns out we have to use a force there as well, but there's got to be a special case for this force. We have a little bit more detail that needs to go into it. So if I have something that's free to rotate, this thing is, and I apply a force to it, say like this, that force doesn't cause rotation. But if I apply that same force down here, suddenly that force does cause rotation. All right, so maybe it's just position. I can apply a force at a certain location, and then it rotates. But if I apply a force in this direction at that location, now the thing doesn't rotate anymore. Or if I apply that same force up here, now it does rotate again. So both the position and the direction of the force seem to matter. Now, we're going to use an idea called, we're going to describe this as the torque being applied to an object. So a torque takes into account both the force with its magnitude and direction, and the location at which that force is being applied. Up until now, we've drawn, say, free body diagrams just as a single point with all the forces acting at that one point. Now, though, it matters where on the object that force is being applied. So when we sketch this out, it's no longer going to work to draw our free body diagrams with just a single point. We have to show how this object is spread through space. Let's try it. Let's say we have just some irregularly shaped object here. And we're going to apply a force to it. And we'll say that force is acting at this location right here. Now, that location matters, but how do we define that location? What's important about that? Well, with this example, it was important that my force this direction was located down here, or my force this direction was located up here. Those things matter because of how this is able to rotate. When I push this direction, this thing isn't able to rotate. No matter how I apply a force, this thing can only rotate around this one axis that goes through the very middle here. So that very center point of this wheel stays right where it is. And we'll call that location the axis of rotation. So a line that goes through that point is our axis of rotation. Before we can do anything with torque, we need to define what our axis of rotation is. Now sometimes it'll be pretty well defined for us already. So with the wheel, there's already some spot where it can rotate about, and it can't rotate about the other positions. Well, unless I say hold it like this, and I'm going to rotate it about some new position here, keeping this place roughly where it is, and rotate about some new axis. So I can define a new axis of rotation for these things. Sometimes it's defined for us, sometimes we have to define it. Let's just say that this one has a pin holding it in place right here. So the whole thing can rotate around that pin. Let's use that as our axis of rotation. So our location for this force then, we're going to describe using a vector that goes from our axis of rotation to the location where that force is being applied. So that vector would point in this direction. And we call that our R vector. R is the position vector. So we have a force vector and a position vector. And then we'll use those two vectors to figure out what our torque is going to be. Now our torque, we'll use a Greek letter tau, and that's a vector quantity. Now at this level of physics, we really only care about the magnitude of that. But just for completeness sake, we'll talk about the vector torque. Now the vector torque we get by doing what's called a cross product of these two vectors. So we talked about dot products already when we did work. Work was the force dotted with the displacement vector, the dot product of the force vector and the displacement vector. Now we're going to look at the cross product of the r vector and the f vector. Since we only care about magnitudes, we don't really have to get into too much detail about what the cross product is and how we figure out direction for that. We're only going to look at the magnitude of torque. So the magnitude of torque we can calculate as the magnitude of our r vector times the magnitude of our f vector, and then we also have this direction piece that matters. We'll have the sine of some angle theta. The angle theta is the difference in directions between the r vector and the f vector. Now that can be a little tricky. On a diagram like this, we might say, well, it looks like theta is right here, but actually that's not the case. That angle would be the angle between this direction and this direction, but our r vector is pointing to the right. So actually what we might do to figure out this angle is just extend this r vector out a little bit. So r points to the right, f points a little bit to the right, but mostly up. Our theta for that equation is going to be right there. Rf times the sine of the angle between those two vectors, that's going to be the magnitude of our torque. Now since torque is a vector, we do need to know a little bit about the direction for this thing. We're going to have only rotation about a single well-defined axis. Here it was this point right there. And so the rotation really is pretty limited here. We can either have this whole thing rotating this direction, or we can have the whole thing rotating this direction. So for us, it's going to be enough to state whether this is going to be a clockwise or a counterclockwise torque. So a torque that's clockwise would tend to make this rotate in the clockwise direction. The thing may not be rotating in the clockwise direction if there are other torques or if there are some initial conditions that are at play here. But the torque would tend to make it rotate in the clockwise direction. This force, though, since it's pointing up in this direction, we can kind of see, imagine we hold this spot in place. This force would make the whole thing rotate in this direction, which is the counterclockwise direction. By convention, we use a positive sign for a torque that causes rotation in the counterclockwise direction, a negative sign for the clockwise direction. But r times f times the sine of the angle between us gets us the magnitude. We have to figure out the direction just by imagining the situation or looking at the picture.
So let's consider now this, this rectangular object that has a force acting on it toward the right side. And maybe we were asked to calculate the torque caused by that force. So there's a few things that we have to know or decide before we can do that. First off, we need to know the magnitude of the force. That's important here. So let's just make up a magnitude here. Let's call this 100 newtons. All right. Second, we need to know the r vector. Now the r vector depends on the location of the force, but it also depends on what our chosen axis of rotation is. So in the absence of a given axis of rotation, we could choose one. Let's just say that our axis of rotation is going to be through a point right here. So we imagine sticking a pin in the rectangle and at that black dot there, and it's going to rotate about that point. So then our r vector is going to go from the axis of rotation, and it does have to go from the axis of rotation toward the force. So it goes in this direction. That's our r vector. And let's say that that's a distance of 2 meters. All right, last thing we need to know is the angle between the r vector and the f vector. And so remember, our r vector is pointing to the right. Our f vector, it looks like, is pointing straight down. So we'll make this our theta, and we'll say that that's 90 degrees. So then the magnitude for the torque. The magnitude for the torque is going to be magnitude for torque equals the magnitude for the force times the magnitude for the r vector times the sine of the angle between those. So that's going to be 100 newtons times 2.0 meters times the sine of 90 degrees, which is going to get us 200 for the number. Now the units on this are going to be newtons times meters. We'll just use Newton meters. Now you might remember that work was also a force times the distance, and we got Newton meters there, but we usually used the units of joules for that. And we'll continue that convention of using joules for work and energy. When we have torque, even though the units are mathematically equivalent, we use Newton meters for our measurement for torque, just so we don't get those confused with some kind of an energy measurement. Now we'll see a little later on how sort of why those units end up being the same. It's not that torque is an energy form or anything like that, but it does have to do with how the energy is changed for rotation, for rotating objects. So we'll come back to that one later on. For now, just know that we need to use 200 Newton meters for that. The other piece to this, though, if we're looking for the torque overall and not just the magnitude for the torque, we do need to state the direction. So the magnitude is 200 Newton meters. And then if we imagine sticking our pin in place right up here and then pulling down this direction, we're going to have this whole thing swinging in this direction. So that's the clockwise direction. And so we can just write clockwise. The convention is usually that clockwise is the negative direction. So this would be a negative 200 Newton meters. We start to see all sorts of parallels between linear motion or translational motion and rotational motion. One more parallel here is that with translational motion, we cared mainly about the net force that acted on some object when we were trying to figure out how that object was going to move or how its motion was going to change. Well, here with rotation, it's not an individual torque that we're going to care about so much as the net torque on that object about some axis of rotation that's going to determine how its rotation is changing. We'll get into more detail on that later on. For now, though, let's just try calculating the net torque acting on this star about an axis of rotation that goes through this point in the middle there. So you're given some r vectors and some f vectors here. We need to calculate the torque for each of those and add those together. We'll be careful about the signs. We'll use clockwise as negative and counterclockwise as positive. And we are going to have to be careful about directions here too, those angles. So if I want to find the net torque is just going to be the torque for each individual object, or for each individual force added together. So the net torque is going to be torque 1 plus torque 2. Torque 1, my towels are getting out of control here. Torque 1 will be the torque caused by force 1, and so that'll be r times f times the sine of the angle between those two. So for our r magnitude on this, we'll have 0.10 meters. Our force has a magnitude of 50 newtons times the sine of, and here's a trap, there's an angle given to you as 37 degrees, but that is not the angle between those two vectors. So vector r1 points to the right, vector f1 points up and to the right, but there's not a 37-degree angle between those two. So I generally will extend my r vector out just a little bit, and then this is the angle that I'm looking for. That's my theta 1. All right, so that one points straight to the right. The other dashed line points straight up, so those two angles must be complementary, which means this is sine of 53 degrees, not sine of 37 degrees. All right, and then we're going to add to that the torque caused by force 2. So that would be R2, which is 0.10 meters, times F2, 100 newtons, times the sine of the angle between those. And again, the angle between those isn't given. It looks like it is because that angle goes from the red line to the black line, but the black, the R2 vector, it really points in this direction. So it's going to be this angle that we're interested in, theta. Now, as far as the sine goes here, that's not actually going to cause a difference. The sine of 60 degrees or the sine of theta here is going to be 120 degrees. Those two are equivalent. The sines of those are equivalent. So it doesn't actually make a difference as far as our result goes, but good practice to get into here. So a sine of 120 degrees. All right. So now we're going to need to calculate these. We also need to think about direction on these, and let's go ahead and do that in this previous step. F1 is going to cause this whole thing to rotate, or we're going to try and make this whole thing rotate in the counterclockwise direction. So that makes this a positive torque. F2 is going to try and spin this thing in the opposite direction, in the clockwise direction, which makes torque 2 a negative torque. So we'll have to account for that when we go to add these two together. All right, so our net torque then, whoops, I'm adding a 1 where there shouldn't be one there. There we go. Our net torque is going to be a positive, let's see, 0.1 times 50 newtons is going to give us 5 Newton meters times the sine of 53 degrees. 53 degrees, remember, is one of those ones that shows up on your green sheet, so we'll just use that approximation. That's 4/5. So 5 times 4/5 gives us positive 4, and the units on that are Newton meters. And then plus, we have a negative sign there. 0.1 times 100 is 10. Units are Newton meters, and then times sine of 120 degrees, which is the same as sine of 60 degrees. So sine of 120 degrees or sine of 160 degrees is not quite such a nice number to work with. It's 0.866-ish, but it is on the green sheet as well. Sine of 60 degrees is square root 3 over 2, but we'll just use the rounded decimal version. And so then that times the 10 that we had earlier gets us to negative 8.66 Newton meters. And so our net torque is going to be a positive 4 and a negative 8.66 Newton meters. That gets us to a negative 4.66 Newton meters, or 4.66 Newton meters in the clockwise direction. So there is a net torque on this in the clockwise direction. Later on we'll talk about what that means and how that's going to relate to velocities and accelerations and positions of this thing in those angular terms.